Organic chemistry without basic is a very big problem, right? Whatever you did, reactant, some reactant is converting, some reagent is there, one substrate is there, it has to convert to product. Different kind of products are there in the options, but still you feels it as a difficulty to choose. Whatever you choose, it is coming as the wrong thing. So there is a reason behind it. Whatever you study in organic, if your basics is not clear, there is a chance that you can go to wrong. But if your basics is very good, then organic is very easy. Within 1 second the problem is done. So we will cover organic one by one. So in today's video we are going to learn about the electrophiles. These all are attacking reagents, okay? Attacking species. Attacking species. Before starting into that, all of you, like when you are studying organic chemistry, don't see it as a structure. Don't see that some carbon is there, hydrogen is there. You have to imagine it as an electron cloud. This carbon or whatever the hydrogen or oxygen, whatever it is a kind of electron cloud. So some electrons clouds are here. These electron clouds will get attracted to wherever the partial positive charge. So this is about the organic chemistry. So there is a particular substrate. That substrate has a reagent and it will form the product. Okay. So this particular attacking reagent can be in different style, right? So one important thing is in that is electrophiles. So in this video we will study about electrophiles, right? Electrophiles. So what is electrophile? As the word suggests, electron loving species. Phile means loving. Electron means just electron density. So these are kind of some species which love electrons. So basically, if it has to love electrons, then it should be electron deficient. So these are electron deficient species. Electron deficient species. So electron deficient species only require electron, right? If it is already enriched with electron, they will repel the electrons. So whatever species, whether it is positive charge or whatever, the concept is that this is the key point. It should be electron deficient. Okay. So now different types of electrophiles you can see. One will be positively charged electrophiles, or the second one is, you can see the neutral species itself, but we can say vacant orbital, due to vacant orbital, right? Third one, octet incomplete. These are the three types of categories of electrophiles you can see. Positively charged, we are going to study about electron loving species. Obviously this positive charge is there. This positive charge is going to attract the electron, right? For sure. If any vacant orbital is there, this orbital is also going to attract the electron. This is also sure. Now suppose there is an octet incomplete. Octet incomplete means suppose any atom, it does not have octet, you know, right? It octet stability. Anything in the vacant orbital, if it has 8 electrons, it is stable. Suppose it does not have 8 electrons, then also it will attract electron. So these are the three possibility in order to behave as a electrophile. So we will see the first possibility, that is positively charged electrophiles. Okay, see, these are very important because in a reaction you should identify what type of reagent it is. If you understand what type of reagent it is, then only you can understand where it will go and attack. So this is very important. Okay, so now we see electrophile, positively charged electrophiles. Positively charged electrophiles. So it's nothing, you just have a positive charge on that. For example, if I am saying CH3 positive, basically how the CH3 positive is forming, suppose this hydrogen is there and the hydrogen has taken with electron, it's not easily possible. It should not be possible from hydrogen. Suppose a Cl is there. Okay, so the Cl has removed from it. Okay, Cl has an electronegative atom, right? So obviously this is an electronegative atom, chlorine. So it will take away these electrons. Suppose it take away the electrons and left this molecule. So that molecule is going to get a positive charge in this. So again, this is an electrophile, or simply H plus. As did right, H plus is a proton. It is also an electrophile. Simply any halogen positive charge. Different ways are there how this halogen positive charge is forming, which you will study in the coming sessions. Any kind of thing which has a positive charge. But is it like anything which has a positive charge is an electrophile? It's not necessary. It's not always necessary. For example, H3O plus. H3O plus. Okay, so I will try to form it directly. You have an oxygen, water. Okay, this is a water. Everyone must be knowing the water structure, right? Now you can see here a hydrogen plus is there, a proton is there. This lone pair has been accepting this proton. Okay, this lone pair is accepting the proton, and what you are getting is hydrogen, lone pair, and the lone pair has been given to H plus. Okay, this is what. This is also H3O plus. Is it an electrophile? It's not an electrophile. First of all, this is not something electron deficient. It has electrons. See here, 1, 2, 3, 4, 5, 6, 7, 8. And did you think that this oxygen can accept one more electron from something? Obviously H plus can, but whether this oxygen as H3O plus itself, will it accept an electron? Let's see. For example, you see here, where is this? Okay, yeah. I'm just taking this H3O oxygen, 1s2 oxygen hybridization. Okay, why I am going through the basics? Because you should understand when it can act as an electrophile. Even if it has positive charge, it is not necessary. It has to accept the electron. So oxygen electronic configuration, if I draw, that will be 1s2, 2s2, 2p4, right? So H3O plus structure you already know. Sorry, H2O structure you already know. That is sp3 hybridized, right? sp3 hybridized. I hope you will be having this basic knowledge, right? So now you see here, this is the valence electron. I am just drawing the valence electron here. Valence shell electrons, okay? 2p4. 1, 2, 3, 4. Now hydrogens are coming. 2 hydrogens are coming. So 2 hydrogens are coming means, like, from hydrogen has to make the bond, but it is not directly going to make like this, because now it is an sp3 hybridized, right? sp3 hybridized, and this particular thing is going to hybridize together. Okay, it is going to hybridize together, and you are going to get 4 sp3 hybridized orbital, in which 2 sp3 hybridized orbitals are already filled with lone pairs, and the other 2 sp3 hybridized orbitals are singly occupied, where hydrogen is going to coming and giving its one electron. So see here, the complete hydrogen came, gave it electrons, it is completely filled. Now oxygen is a second group, it does not have 2d, guys. 2d is not there. So if one orbital is not there, then how it is going to accept the new electron coming? It's not going to accept. So it is very important. It's not just a positive charge, it's about whether it accept, whether is there a space to accept the electron. So H3O plus is not an electrophile. The same way, what else species I can say in second group other than H3O plus? I can say NH4 plus. The same reason, NH4 plus is also not a electrophile. Sorry if I said as nucleophile, but H plus is. So this is the first criteria. All other any kind of positive charge, it is, if it has a vacant orbital, definitely it is a electrophile. Now other possibility, the second one we know, What is the second one? Second one is neutral but having vacant. Neutral but have vacant orbitals. Neutral but have vacant orbitals. For example, you consider BF3. Guys, it is octet incomplete, right? Fluorine. What is its hybridization? sp2. 3 sigma bonds, sp2. So one p orbital is the which is unhybridized. So suppose an electron is coming. This electron can be accepted in this vacant orbital. Therefore, it is an electrophile. The other one, it's not always vacant p orbital. It can be vacant d orbital also. It can be vacant p or vacant d. What is the example of vacant d? For example, suppose any other thing I am taking. Like suppose, which will I take? Is PCl5. Okay, can I take the PCl5 example? PCl5. How the PCl5 is going to accept the electron again? Okay. Cl. See, it's completely filled, no, right? 5 bonds, total 10 electron, more than octet. Now, how it is going to act as an electrophile? Obviously, electron will come and attack and one Cl can leave. But where it will come and attack? If all the electrons are already filled, it's very difficult to come and attack, right? So, see here, in PCl5 or simply SO3 also you can take. Okay, PCl5, what is the first electronic configuration? 2s2, 2p3, right? 2s2, 2p3. 3s2, 3p3. It's my bad. Like this, right? 5. So 5 chlorine is coming. So 5 chlorine is coming in the sense 4 orbital is not enough and there is completely filled. Chlorine has to need a space to give one electron. Only 3 is there. So what it will do? This is actually the basic of chemical bonding. So this is going to jump here and like this, right? Now it has how many? 1, 2, 3, 4, 5. sp3d, right? sp3d. Now all the chlorine will come and give it, right? All the chlorine is coming and giving its electron there. Now you see here, guys, it has vacant d orbital. So to this vacant d orbital, the electron can be accepted. Same in the case of SO3. Example, S double bond O. This is also an electrophile. Obviously, it should, in order to act as an electrophile, there is a partial positive charge should be created, which this oxygen is an electronegative atom. So it will pull the electron. So partial positive. So definitely it is going to attract an electron. Partial positive charge is there. Now SO3, you know that its hybridization is sp2 because it has 3 sigma bonds. Now you see sulfur 3s2, oxygen family 3p4, right? 1, 2, 3, 4, and it has 3d. Obviously it has 3d, but it's not filled, right? Now you see here how many bonds actually total it is making. 1, 2, 6 are there, right? So I'm pulling this here. I'm just making it jump here. Now these are sp2, which is going to make oxygen sigma bond. Now you see here, this p orbital will make pi bond with oxygen, whereas this two will make pi bond with oxygen. D pi we can say. D pi and p pi. Oxygen p orbital. Oxygen does not have p pi. Still there is vacant orbital, guys, right? So these vacant orbitals is used to make the to act as an electrophile, right? So this is also one chance. Now what is the next example? The next example is for which one? Incomplete octet, right? Sorry, which all we discussed, right? Let me see here, 1 second. Octet incomplete, yeah. Octet incomplete. Octet incomplete. Already we have seen one example like BF3, but there is a special example, very very important, CCl2 dichlorocarbene or simply carbene, CH2. These are carbene, guys. By looking at it, it has lone pair, so you feel like it's an electron rich species, but actually it is not electron rich, it's an electrophile. Why it is so? Because you see here, if I am drawing here like this, 1 2 3 4 5 6 and 1 2 3 sp2, and it has a vacant p orbital and it is electron deficient species. Octet is incomplete, therefore this is electron deficient. Since it is electron deficient, it will always seek the electron in order to attain the stability. Therefore this is also an electrophile, very very important. So seeing just an electron cloud doesn't means it will be a nucleophile. It may also can as an electrophile. It may electron deficient, so very clear about that. Next, if I am saying about, there are octet complete species also, because of some reasons it will act as an electrophilic center. Okay, electron loving it's not as an electrophilic center, it can also act as an electrophile, electrophile, where it attract the electron. Okay, electrophilic center and nucleophilic center I will separately talk it later. Now for example, if I say here, you say guys, if I am saying a molecule like CO2, is it an electrophile or a nucleophile? It can act as an electrophile because of the partial positive charge here and a pi bond here. This pi bond is weak and it can be easily break. For example, if an electron is coming, any electron rich species is coming, this electron rich species can be get attracted to the partial positive charge on this, and the pi bond, a weak bond, can break. For example, you can see here, if this is coming and attacking here, this pi bond will break and this can go like this, some new species. Okay, so this is also an electrophile. So these are the basic examples of which all can act as an electrophile. Looking at just that, you can understand whether it is an electrophile. For example, if I draw a benzene, everywhere you are just saying a electron cloud, it's not going to act as an electrophile, and obviously it is not electron deficient species. Everywhere octet is complete. So when you are saying a species, in order to understand whether it can act as an electrophile or not, these are the main thing. You should check whether it is having a positive charge and it has a vacant orbital to accept, whether it is having any vacant orbital, and whether it is incomplete octet. So these are the three things which you have to look at it when you are saying it as an electrophile. I hope everyone understood this. So in the next video we will know more about the nucleophiles. Thank you.